In this video, we're going to continue our discussion of Le Chatelier's principle. So we know that Le Chatelier's principle tells us that if a stress is applied to a reaction mixture that is at equilibrium, the net reaction occurs in the direction that relieves that stress. Put another way, if a reaction is at equilibrium and we disturb the equilibrium, the reaction will proceed either in the forward or reverse direction in order to restore equilibrium. Now we know that we can disturb an equilibrium three major ways. We can change the concentrations of the reactants or products. We can change the pressure and therefore affect the volume, or we can change the temperature. In this video, we're going to look at the relationship between changing the pressure and volume and how that affects our equilibrium. So just briefly, if we remember our gas law, we know that if we have say we have a reaction mixture that contains gases, and that's very important, it must contain some moles of gases, at a certain pressure and a certain volume. If let's say we change the pressure, let's say we double the pressure, if we increase the pressure, the volume will decrease. So put another way, the volume and the pressure are inversely related. An increase in pressure will decrease in volume. Or if we were to decrease the pressure, the volume would expand or go up accordingly. So through this discussion, remember this relationship. The pressure and volume are inversely related, assuming that the moles and temperature remain constant. So in general, when an equilibrium is disturbed by a change in volume, which results in a corresponding change in pressure, Le Chatelier's principle tells us that increasing the pressure by reducing the volume will bring about the net reaction in the direction that decreases the number of moles of gas. So if we increase the pressure and therefore decrease the volume, the equilibrium will shift, or the reaction will shift in a direction that decreases the total number of moles of gas. Conversely, if we decrease the pressure and therefore increase the volume, this will bring about the net reaction in the direction that increases the number of moles of gas. So which direction the reaction shifts depends on the number of moles of gas on the product and reactant side. So that's what we want to talk about, and let's try to explain that a little better. So for our example, let's look at this reaction, and our stoichiometry tells us that on our reactant side, we have 4 moles of gas, so 1 mole of nitrogen for every 3 moles of hydrogen. So 4 moles of gas on our reactant side for every 2 moles of gas on our product side. So that's important to keep track of because that's going to affect the direction of our reaction shift when we disturb our equilibrium. So let's look at an example to help us illustrate this. So for this example, again, we're going to be using this reaction, nitrogen plus hydrogen is in equilibrium with 2 moles of ammonia. So let's say we had that reaction mixture in a container and our reaction is at equilibrium. And we disturb that equilibrium by increasing the pressure. So we increase the pressure, and that of course results in a decrease in volume. Okay, so we had our reaction at equilibrium, and we increased the pressure and therefore decreased the volume. Well, now our reaction mixture is no longer at equilibrium. In order to reestablish equilibrium, the net reaction will proceed in the direction that decreases the number of moles of gas. So Le Chatelier's principle tells us that the reaction will shift in order to decrease the number of moles of gas. Remember, over here on the reactant side, we have 4 moles based on our stoichiometry for every 2 moles of product. So which way will the reaction shift in order to reestablish equilibrium? Well, our reaction will shift from left to right because we have fewer moles on the product side compared to the reactant side. So in this example, we have a reaction at equilibrium. We increase the pressure and therefore decrease the volume. Our reaction will shift from left to right in this example because it's shifting towards the side with fewer moles of gas. let's take a look at another example. Using the same reaction, we have our reaction at equilibrium, and let's say we disturb our equilibrium by decreasing the pressure, which results in an increase in the volume. Well, if we do that, if we change the pressure, decrease the pressure, increase the volume, our reaction is no longer at equilibrium. And Le Chatelier's principle tells us in order to reestablish equilibrium, the net reaction will proceed in the direction that increases the number of moles of gas. So increasing the volume, the gas particles tend to expand. There's going to be more room for the gas particles to form. And so our reaction will shift from right to left in this example in order to produce more moles of gas and therefore reestablish equilibrium. Now we can also look at this numerically by comparing Kc and Qc. So let's take just a minute and do that. Let's use our same reaction as an example. And let's say we had an equilibrium mixture of this reaction, and we had these concentrations: 0.5 molar nitrogen, 3 molar hydrogen, 1.98 molar ammonia, and these are equilibrium concentrations. And we disturb this reaction equilibrium by reducing the volume by a factor of 2. Which way will the reaction shift? And let's see if we can predict that using QC and Kc. Now, just based on this, if we reduce the volume, Le Chatelier's principle tells us that our reaction should shift from left to right in the direction of fewer moles. So let's see if we get that result. So remember, by decreasing the volume, we should shift in the direction of the fewer moles. So back to our numbers here. We have a reaction at equilibrium. So we have a Kc expression, and we can plug in these equilibrium concentrations. I've just plugged in my equilibrium concentrations and calculated my Kc value. So my Kc value for this reaction is 0.291. Now, we disturb the equilibrium by reducing the volume by a factor of 2. When we reduce the volume, that's going to disrupt the equilibrium. So by reducing the volume, the reaction is no longer at equilibrium. Important to note, though, we haven't changed the moles, just the volume. The moles have not changed, but by reducing the volume, the molarity will double. And so the molarity of each species in the gas phase will double. So remember, molarity is moles per liter. We haven't changed the moles, but we decreased the volume. So if we decrease the volume, numerically the molarity should increase or double. So when we reduce the volume, the molarity of each species in the gas phase only, will double. So now we have our reaction. We've changed the volume, we've reduced the volume, we're no longer at equilibrium, and all of our equilibrium concentrations have doubled because of our change in volume. So we can plug those new concentrations in. This would be 1, this would be 6, and this would be 3.96, and I've plugged those into a QC expression since we're no longer at equilibrium. And now we can calculate our QC value. Well, we can compare our QC to our Kc for this reaction at a given temperature, and we see that our QC is smaller. So by reducing the volume, it results in our QC being smaller than Kc. Well, we know if QC is smaller than Kc, more reactants will be consumed and the net reaction will shift from left to right. And that's what we predicted to begin with, just based on the number of moles. But here we're showing that numerically it holds true. So if you have a reaction of gaseous substances like we had here, and QC is equal to Kc, well, we're at equilibrium. If we decrease the volume by increasing the pressure, that results in QC being less than Kc. And so the reaction will shift from left to right in order to reestablish equilibrium and get QC back to Kc. So take a look at this problem. For each of these reactions, does the number of moles of product increase, decrease, or remain the same when each of the following equilibria is subjected to a decrease in pressure by increasing the volume. So if we decrease the pressure and increase the volume correspondingly, what will happen to the moles of my products? Will they increase, decrease, or stay the same? Pause the video and predict that. Okay, so let's take a look at the first one. For the first one, we have 1 mole of gas over here, and we have 2 moles of gas over here. So if we decrease the pressure, increase the volume, Le Chatelier's principle tells us the reaction should shift towards the side with more moles of gas. So we would predict the equilibrium to shift from left to right, and therefore my moles of product should increase. The second one, well, this is calcium oxide is a solid, calcium carbonate is a solid. We only want to look at the moles of gas, and we only have one gas here, carbon dioxide. So if we decrease the pressure by increasing the volume, the equilibrium will again shift to the side in order to produce more moles of gas. So the equilibrium or the reaction will shift from right to left in order to reestablish equilibrium. So my moles of product will decrease. Now, remember, the concentration of calcium carbonate will remain the same, but the moles will decrease. So we can change the moles, but the concentrations are constant. Please be sure you're aware of that. So here we have the moles of product would decrease. And finally, if we look at this one, we have 4 moles of water vapor over here and 2 moles of hydrogen. Again, we want to focus only on the gas. So our moles are the same. So if we change the volume and the pressure, well, which way will it shift? It's not going to shift either way. So in this case, it would remain the same since we have the same number of moles of gas on the product and reactant side. So be sure you're familiar with Le Chatelier's principle and how equilibrium is reestablished when we change the volume and pressure.